Okay, good morning. We were discussing models of MOS transistors. So the new things that you may not have been familiar with is firstly that it should be modeled as a 4-terminal device, and what is conventionally done, it's easy for at least for use with analog circuits, is so you extend the 3-terminal model with Vt as a function of VSB. Okay. We'll see. This is not the only way to model it. In fact, this is not probably the best way to model it either, but for hand calculations, this is what we'll use. And the second thing is this sub-threshold conduction or weak inversion operation. Okay. Now, strong inversion, which is where this square law is expected to hold. This is when VGS minus VT is greater than about 6 times the thermal voltage. Okay. Right. How much is 6 times the thermal voltage? How much? 0. How much is 6 times the thermal voltage? 150 millivolts. So if you have this, by the way, this VGS minus VT, it's also called overdrive. That is, you have VGS equals VT, it turns on. How much you go above that? That's called the gate overdrive. If it's over about 150 millivolts or so, you can say it is in strong inversion. Now, below that, you get into moderate inversion, where you have both drift and diffusion type of current, and then weak inversion, where you have this exponential behavior. Okay, this is square law, right? And this weak inversion, again, you can use it because in weak inversion region, you get the highest GM for a given bias current. On the other hand, it can also be a problem in the sense the transistor never really turns off. So you will always have leakage current in any circuit. Okay. Now it is because of this concern that in modern processes, you have transistors with many threshold voltages options available. Okay. So if you have a high threshold voltage, your leakage will be small. Okay. Because for 0 volts, you will be operating with a larger negative VGS minus VT. Okay. At the same time, if you have a higher threshold voltage, the current that you get, the maximum current that you can get will be smaller. So the speed of the circuits will be less. Okay. Especially when you come to very small supply voltages, 1 volt or under, right? So you will need these options, because when you had high voltages, then you can have maybe a single transistor and then use a variety of circuits to get what you want. But here you will need that. So this is one of the reasons why you have multiple VT options in modern processes. And this, if you have a high VT, this means high speed, also high leakage. As I mentioned, there may be applications where it's the standby current that determines the average current drop from the battery, not really when it's being used, because it's used so infrequently that it's the standby that dominates the power consumption, current energy consumption. Sorry, I think I inverted this. This is low VT. Low VT means you have higher currents and higher speeds. And if you have high VT, this will have lower speed and also will have low leakage. Okay. Now, just a small diversion. I will use the 3-terminal model. I mean, I'll show the only 3 terminals wherever the 4th one is not required. Now, of course, for the transistor to be on, VGS must be greater than the threshold voltage. Okay. What is the condition for saturation region? VDS greater than VGS minus VT. Okay. Now, if I had to express this, the second condition, instead of with VDS, I want to express it in terms of VGD. What does that mean? VGD? Yeah. So if you just rearrange this, VGS minus VDS on the right side and VT on the left side. So VGD should be less than VT. This is for saturation region. Okay. So what does this really mean? I mean, and obviously, like for the triode region, you should have VGS greater than VT and VGD also greater than VT. What does it mean in terms of device operation? That is, what do these two regions mean, or what does the triode region mean? Many times it's useful to think of the triode region like this, instead of terms of VGD instead of VDS. What is really happening? Triode? Yeah. So basically, if both these voltages are greater than VT, you will have the channel formed all the way from the source to the drain. Okay. I mean, saturation, what happens is at the drain end, actually it is off. Okay. Whereas at the source end, it is on. The current flows through the channel, and actually there will be a depletion gap there, and current just shoots through that, and then you have the current. So basically, the saturation means that drain end is actually turned off. That's why the drain voltage doesn't influence the current anymore. Okay. So channel is not directly connected to the drain per se, so it doesn't really influence the current. Okay. I will, for simplicity, I'll call this terminal D, G, and S. And let's say I plot VGD and VGS. Okay. And I mark the threshold voltage on both. Right. And I will divide this into 4 regions. What is happening here in this region, where VGD is less than VT, VGS is less than VT? What region is that? Off. So this is the cutoff region. What is this region, where both are greater than VT? This is when the transistor is in the triode region. Okay. What is this region here? This one? saturation. Okay, and this one, what is that? Off. What is this region? So this region, fine. This is saturation. What is this part? What region is that? Off. Yeah. So basically here I still call this D and S, but what is happening is the current will be flowing from bottom to top. It is the saturation region, but with the bottom terminal being the drain and the top one being the source. Okay. So the transistor is a symmetric device. Right? Is this clear? Why that's the saturation region? I have labeled these terminals as D and S. If I call it V1 and 2, then so maybe this will be VG1 and sorry, this is VG1 and this is VG2. So in this case, 1 is drain and 2 is source, whereas in this case 1 is source and 2 is drain. Okay, is this clear? So this happens in during circuit operation. This can happen. Of course, hand calculations with this, you have to analyze the two cases separately and so on. But these things can happen. Okay. So the transistor, the standard MOS transistor is a symmetrical device. By looking at the device, you can't tell which is the drain and which is the source. Okay. In fact, we see that that is sort of advantageous when it comes to layout of the transistors. We'll be able to do that in a convenient way. Okay. Now also, because the device is symmetric, it makes sense that the model also be symmetrical. The way we have it, it is asymmetrical. We have something special called the source and we refer everything to the source. But actually it turns out it is, it came, first of all, the other transistor which came before the MOS transistor was the bipolar transistor, and that is truly an asymmetrical device. Their collector and emitter are different. Okay. And there the model referred to, model had voltages referred to the emitter. So when the MOS transistor came, the same thing was continued. Okay. And for analog, it sort of makes sense. Typically, you bias it such that one side is more positive than the other and then operate like that. So you can distinguish. But the device itself is symmetrical. So it is also useful to have a symmetric model. And in fact, the asymmetric model does have some problems because you have to check which is the drain and the source and switch it. And many of the earlier models had all kinds of discontinuities when this VDS crossed 0. Okay, it should actually be symmetrical. Whatever it is, we may or may not be able to write the expression for it, but clearly it should be symmetrical. And it turns out it is, and that we can realize by simply manipulating the expressions we have. So the triode region equation is mu Cox W by L VGS minus VT square minus VDS square by 2, right? Sorry, VGS minus VT times VDS minus VDS square by 2. Okay. In fact, let me let's see what is the easiest way to show this. So this is of course a factor. So this can be I think the other way, right? VDS will be VGS minus VGD. Okay. Okay. So now let's see what is the easiest way to manipulate this. This actually you can do the algebra yourself. It is quite simple, but let's see if I already have it here. Yeah. So instead of referring voltages to the source, we can refer everything to the bulk. Okay. So that makes it symmetrical, right? So we have VDB, VSB, and VGB as well. Okay. So now you can write VGS will be VGB minus VSB, and VDS will be VDB minus VSB. So if you write it, you can try to do this yourself, because this is just some information. I don't want to spend too much time on it. So this whole thing can be changed into half of sorry. Again, I inverted the sign. Okay. So now you can see that you can try this. If you don't get it, I'll work through these details. This is some algebraic manipulation, that's all. Okay. So now you can see that this is of the form of f of VGB, VSB minus f, the same function of VGB, VDB. Okay. Now this is a special form, because in general, of course, you expect it to be a function of all three, right? Okay. You just expect the current to be just function of three voltages that are there, VGB, VDB, and VSB. But it turns out it is actually has a special form where it can be split into some function of VGB and VSB minus the same function of VGB and VDB. Now here, this has to be interpreted properly. This, when I write this as square, what it means is, if the argument, if VGB minus VDB minus VT, okay. If this is less than 0, then I mean you don't take the square of that negative number, that function itself is 0, okay. You understand? So essentially, what is this after all? This you can tie with the other interpretation I gave you. What is this? The first two terms, the combination of the first two terms? VGS. So you have VGS minus VT whole square. So if VGS is less than VT, that end is turned off. So this part of the function will be 0. Similarly, if what is this? VGD. So if VGD is less than VT, this part will be less than 0. And actually, you shouldn't take the square of that. You just take 0. That's all. Okay. So this will give you exactly the same relationship, and this is symmetrical. But of course, we have been using the other one for design for ages, and all the references are like that. We'll continue to use that. But you should know that the MOS transistor is symmetric. And this also, now there is no business of interchanging of drain and source and so on. What happens is, if VSB is greater than VDB, the current will flow one way. If VSB is less than VDB, it will flow in the other direction. That's all. Okay. Is this fine? Yeah, both. Yeah. So you can relate it to this picture. So In this part, both of them will be non-zero. In here, both will be 0. And here one of them, the one related to the source will be 0. Here, the one, one related to the drain will be 0. And here, the one which has VGS will be 0. Okay. Sorry, not VGS, VSB. The one that has the source side, that will be 0. Okay. Any questions about this? So the MOS transistor is a symmetrical device and there is a symmetrical model and many of the simulators have this. Okay, this is something that is useful to know because as you read the literature on analog ICs, you will also come across this. Okay. Yeah. Right. It will become negative if no, in this model you don't need to, right? All that happens is if the drain voltage is higher, the current flows this way. If this is what you call the source, that's why I mean I don't want to introduce unfamiliar terminology by calling them terminal 1 and 2. If this terminal is higher, current flows this way. If this one is higher, current flows that way. So either of these two could be, one could be higher than the other, right? So whatever you call as you have defined one direction. So if this comes out negative, it means that the current is flowing in the other direction. But the current that you calculate will be correct. Okay. With this. So you don't need to worry about which is the quote unquote source and drain here. Okay. Okay. So this is about sort of extra information about MOS model that you are probably not aware of before, the weak inversion stuff and so on. Oh, actually there's one more consideration. So let me, any questions so far about anything that we have discussed like weak inversion or the symmetric model or the body effect? Yeah. Right. So this VT will be different from that one. So now if you look at the, again, the current in the triode region, the expression for current in the triode region, it is, I'll write it like this, times VDS. Okay. So now you have inversion layer from here to there, and VDS is the applied voltage. This is the gate. Okay. How do you get this expression? Have you seen the derivation of this? How do you get this? How many of you seen the derivation of this? Yeah. How do you get this expression? What is the origin of this? Now, what is current? What is current actually? What's the definition of current? Rate of flow of charge. Okay. So now how do you, if you have to determine current, what do you need? You need to know the charge density and you need to know how fast it is going, right? Okay. So how fast will it be going? What is the velocity? Huh? Mobility times electric field. Okay. So what is the electric field? Electric field in which direction are we talking about now? Huh? Okay. So what is the electric field? VDS by L. That's all, right? So this is the channel length. So it will be mu times VDS by L. So this is the electric field and this is the drift velocity. Okay. And what is the rest of it? Charge. So the charge density. So first of all, what is the Cox? It's the capacitance per unit area, not the total capacitance, right? So the charge density would be W Cox times, I mean, this is the capacitance, right? I mean, this is the capacitance per length. So then this times the voltage across the capacitor, right? What is the voltage across this capacitor? It's VGS, I mean, it's that voltage minus VT. That VT comes about because of different semiconductor materials. Although you apply the gate voltage here and the source voltage there, and all these places you will have some other drops, right? That's how you get that VT. VT is the sum of all those extra drops. Okay. So it should be VGS minus VT. Only thing is the voltage difference here is different from there. Okay. So the average charge density will be sort of VGS plus VDS by 2 minus VT. Okay. So that's how you get this. That's how you get this VDS by 2. Okay. Right. So this is the charge density in the lengthwise direction. Okay. So this is how we get it. You calculate the charge in the channel and you calculate the velocity by multiplying the electric field with the mobility. Okay. Now what happens is, what is saturation? Saturation is when this charge density stops being dependent on the drain voltage. Okay. So at that point, actually here also this what matters is not this VDS, but as I said, that side is off. There is that pinch off point. At the end of the channel, what you would have will be exactly VGS minus VT. Okay. So that's how you get, when you multiply the two together, you get the saturation current to be mu Cox W by 2L times VGS minus VT square. Okay. So this one, there is a limitation here also. Again, you may or may not have seen this. If you plot the velocity versus the electric field, what should it be? What should this curve be? Drift velocity versus electric field? Straight line. Okay, and the slope will be the mobility mu, right? Does it follow this, or do you know something else that happens here? So the velocity actually saturates. Okay. So there will be something called Vsat, right? So the velocity doesn't go on increasing. So that needs another modification to the model. Again, this model we probably will not use for hand calculation too much, except when you simulate the transistor, you find that it's most likely not following square law, unless you simulate a very long channel transistor. Okay. Whether it saturates or not depends on how much mu times VDS by L is there in the first place. Okay. So you expect that when you go to short channel transistors, that is small L, you have a greater chance of this happening. Okay. So you will have to modify this, and so what modification will you have to do? So now you know the different pieces of the ID expression, right? So what are all the things you need to modify? Huh? So first of all, again, we'll only look at the expression in the saturation region, because of course independent of L, right? If you set VDS equal to 0, obviously the electric field is 0 and there is going to be no velocity saturation. You can always find a sufficiently small value of VDS where it doesn't happen. So where it really matters is in the saturation region where you have a large VDS. Okay. Saturation current. Now we are talking about with velocity saturation. Okay. So first of all, this mu times VDS by L, this should be changed to VSAT. I think I used uppercase here. It is VSAT. Okay. What else? Yeah, but what should that VDS be in the saturation region? Yeah, what is that VDSAT? Hmm? No, that we've already done, right? So that is this entire the initial factor. This is the velocity that will simply write VSAT there. That's all. Okay. This is the velocity, right? Okay. Instead of that, we'll write VSAT. And then here, if you look at it, inside you will have this VDS by 2, and then you have to substitute that by VGS minus VT. But the point is again, that doesn't happen at VGS minus VT. So basically the modified and this VDS for the saturation region will be simply L times VSAT by mu, some fixed number. Okay. So all we need is now to put these things together. So you will have W Cox VGS minus VT minus L times VSAT by mu times VSAT. Okay. Sorry, I think I made a, huh? No, it is, so that VDS, this expression is for the triode region, okay? You have to substitute that with whatever is related to that point in the saturation region. So here saturation is happening because of velocity. So that is what, where will you put the voltmeter? No, that even in the normal case, you cannot measure the point at that pinch off point using a voltmeter, right? No, if you measure it at the drain, it will be VDS, whatever you apply. Yeah, of course. Yeah. So this is for the expression of the saturation current. Okay. So now what differences do you see between this and originally, of course, what did we have? We had ID to be mu Cox WL VGS minus VT square by 2. Okay. What are all the differences? What are all the differences? First of all, it's not square law anymore. Okay. Then and the current is not inversely proportional to L. Okay. It changes with L in some way. It's not inversely proportional to L. Now, of course, you have to be careful. It's not as though the MOS transistor is operating with this expression and then abruptly it switches to the other one. Okay. So as you go on increasing VDS, as you go to higher field values, you will have some sort of transition from this one to that one. So if you look at the MOS transistor characteristics, it will be somewhere between square law and linear. Okay. So that's what you're going to get at very high fields it will go closer to being linear, and at lower fields it can be closer to square law. Okay. And in any process, you can always get to some sort of this square law type region if you use very long channel transistors. Okay, because if you use very long channel transistors, the field will be low, right? So you can operate it without velocities as well. I mean, it's not something I would desire to do. Okay, but all I'm saying is that if you take a very long channel transistor in any technology, you are likely to observe the square law behavior. Okay, but at shorter channel lengths, you will not do that. And then there are lots of other complicated effects which I won't get into. But again, this is something to be aware of. So if you simulate the characteristic of a MOS transistor, you're not going to get square law. You'll get something in the middle. The other thing is the current is proportional to W, but not inversely proportional to L. Okay. And this is something to keep in mind while making current mirrors and other things. Okay. Whenever you want any matching, you would not use, let's say you want half the current in a current mirror. You can either use half the width or double the length according to square law, but the double the length simply doesn't work. Okay. So you have to use all transistors of the same length and then change the W in proportion. In fact, we'll see how exactly we should do that. Okay. So these are all the things that you need to keep in mind. And as somebody pointed out, GM is basically independent of bias, right? Because if you differentiate this expression with respect to VGS, you will basically get a constant. Okay. So by increasing VGS, you cannot get more GM anymore. The only thing you can do is go on increasing W, right? This is proportional to the width. Okay. So this is what you would see. Okay. With long channels, you tend to see square law. Okay. Now, this is about as far as we go with model details and so on. We'll need to be aware of these things. So again, I emphasize that the point of all the equations is not to do exact calculations, because the circuits that you will design eventually, even something like an op amp will have some 20 transistors, and you're not going to put the equations for all those transistors together. Okay. The point of all this analysis is when you start with the design, you will get something and you will have to move the design in the right direction. It may be deficient in some way, it may be consuming too much power, it may not have enough gain and so on. So you will have to move it in some direction. So that's what you will have to do. Okay. So other things you're already aware of, that the small signal output conductance of the MOS transistor, it is basically dependent on the length of the transistor. So if you want high gain, you have to use long channels and so on. Okay. So any questions on any modeling related stuff that we have discussed? So body effect is something probably new, and then maybe the weak inversion operation. Okay. Now let's go to more design related aspects. So what is it that you actually design when you design ICs? Essentially, you are making two-dimensional drawings, okay, of everything. So the transistor cross section looks like this. If you look at it from the top view, which is what you will be designing, this is what it will look like. Okay. So there will be a rectangle for the gate and rectangles for the source and drain regions. Okay. So let's say this is the source, this is the drain. Okay. And this is the length of the MOS transistor. And what is the width? The width is the width across which the current flows. Okay. So that is the width. And of course, you will have some the gate extending outside because you have to make contact to the gate and so on. Okay. So everything you do is in these two dimensions. Like I said, you have all these layers starting from this diffusion to the gate to various metal layers, and then you make two-dimensional drawings. And that dimension you have control over within some constraints. Because of manufacturability, there will be some minimum and maximum limits for width and spacing and so on. But otherwise, basically, you make 2D drawings of every layer, and you can connect layers to one another through what are known as vias. So that's what you will be doing. Okay. And because of that, lot of even the familiar parameters are described only with those two dimensions, because this third dimension you don't have any control over. Okay. You can't control how deep this is. It's a property of the technology. It's just given to you. Okay. So in the MOS transistor, it's very clear. Anyway, we had W and L, and when you go to design, you will see that there'll be you may have to you will need to know the rules about how long this must be and so on. Okay, there will be some minimum constraint. We don't have to worry about it now. Okay, and also any component comes with like bunch of other extra components. We already saw that. That is, you have a MOS transistor, but you don't get only the MOS transistor. You get those diodes, right? You will get these diodes. Now, of course, you keep them off by making sure that the substrate potential is the lowest in the circuit. But even when they're off, they will be contributing capacitance. Okay. That is, they will, when the off diode is basically the depletion region is like some insulating layer, and then you have the depletion capacitance of the diodes. So if you, the MOS transistor is like this, okay, and the small signal model, the standard small signal model would only be these three, and at low frequencies this is fine because capacitances don't have any effect. So this is the gate, source, drain, and the bulk. There is no current flowing. This is GM-VGS. This is a conductance GDS, and this is GMB-VBS. Okay, and each of these, you know how to relate to the dimensions of the transistor and the operating point, right? Okay, so that we already done. Actually, GMB I have not done, but it's quite easy. So you have the drain current as a function of VGS, VDS, and also VSB, right, through the threshold voltage. Okay, that also comes into the picture. So now what is GM? It is partial derivative of ID with respect to VGS. And what is GMB? It is the partial derivative of IB with respect to VBS, okay, which is that, okay. Now, if you use the square law model in the saturation region, this is what we have, right? Now, the VSB appears through this VT, okay. So this can in turn be written as right. Is this okay? Now, how much is this? What is that? What is that? I mean, how is it related to some other small signal parameter? What is it? It is GM, right? That's all. So it's basically GM times this, and this one you can calculate from So you know this GMB also, I had not explicitly mentioned this. So you can calculate all these small signal parameters from the, basically you need to know the operating point and the dimensions of the transistor, right? Now, in the small signal model, you will also need to add this CGS and CGD. Now these are inherent to the MOS transistor. These are not extra, right? Because the heart of the MOS transistor is the MOS capacitor. Okay, that Cox times W by L that you get, Cox times WL that you get. So whenever you have a MOS transistor, you will always have the CGS and CGD. Okay, so these are intrinsic, but there may be extrinsic parts also. That is, you have some metal connected to this and some other metal connected to the drain or the source, and because they are next to each other, you can have capacitances. All these will have to be modeled. Okay, so there will be a lot of parasitic capacitances, and there will also be the reverse bias capacitances of these, which will basically go from, this is CDB and this is CSB. Okay, so these will also be there. All these will have to be known, and to calculate this CDB and CSB, you will need to know the something about this junction, right? Okay. So, and a junction like this will have, let me just show one junction by showing it as a neat rectangle. Okay, so this is the cross section view, and this is the top view. This is the width, and this is something I'll call LD. It's the length of the junction. It depends on the technology, it will be given to you. Okay, it is LD. So now there are two contributions to this. This depth is fixed. Okay, so we won't get into all of that stuff, but that depth will be fixed. So now there is a capacitance from the bottom part, and there is a capacitance from these side walls. Okay, so very clearly, if you, it's very easy to see that the capacitance of this bottom part is related to the area, right? So this is capacitance per area of the bottom part, and the capacitance on the sides will be related to the perimeter. Okay, so this is now capacitance per unit length. It will have TD inside it. Okay, that will include TD inside, but we don't have to worry about it. Like I said, all the parameters will be given to us so that we only look at the dimensions that we design, which is L, W, LD, all of these things, and calculate from there. Okay, so this is the sidewall capacitance, and this is nothing but the perimeter, right? So again, the reason this is sort of more of this information, not analysis or anything, but when you start designing, if you go to a simulator, you will see all these parameters. You need to know what they are, okay, and also why they are defined the way they are. Okay, so you will be given these things, and depending on the drain source area and the perimeter, you will have to calculate these parasitic capacitances and put them in. Okay, so this, yeah, that's basically what the idea. If it is much deeper than the channel, I mean, it will be quite complicated in that the depletion is not uniform on all the sides, but for our calculations, that's fine. Okay, so we will go through some of this stuff related specifically to IC design, even for resistors and so on. I mean, resistor is very familiar to all of you, but we'll describe the, I mean, the parameters are given in a way that makes sense for this two-dimensional drawings. Okay, so we'll do that, and after that, we'll get into the real design stuff. Okay. Okay then, see you all.